It's going to be by Alexei Rybkin from the University of Alaska Fairbanks, and he's going to tell us something about what KdV does to embedded bound states. Alexei, the stage is yours. Please go ahead.
Thank you. Thank you for your kind invitation. It's very nice to speak at this conference. It's a bit early where I am. It's 6:30 in the morning, so I might be a bit fuzzy. And how much time do I actually have?
You have 1 hour.
1 hour, including questions?
Yes.
Okay. So I have to wrap up about 5 minutes before, right?
Yes.
Okay, well, I'm going to, my talk will address 2 questions. How embedded bound states affect the inverse scattering problem for the full-line Schrödinger operator. And secondly, how KdV evolves such initial profiles, or put it differently, what KdV does to embedded bound states. And so the main object of my consideration is going to be the KdV equation, which I write down in the standard form, and some initial condition. And I'm not going to discuss the history of this famous equation, and chase to the subject matter, which is inverse scattering transform for KdV equation when the spectrum is more complicated than in standard problems. And Fourier inverse scattering transform, or IST for short, is nonlinear Fourier. Conceptually, it is a linear Fourier transformation, but it requires some nonlinear steps. And the first one is direct transform, as you know. Given initial data, we associate with it the full-line Schrödinger operator, and then solve either direct scattering problem or perhaps spectral problem, and find what we call scattering or perhaps spectral data, and then find its time evolution under the KdV flow. Typically, it is a simple linear ODE, and then we solve the inverse problem. It's depending on type of initial profile. It's either inverse scattering problem or inverse spectral problem, which allows us, given time, evolve scattering data or perhaps spectral data is to recover the potential, which solves the KdV equation. And as you know, this machinery runs smoothly in 2 basic cases: short range, when the decay, the initial data is like this, or periodic. We call such conditions standard, and main results related to KdV were obtained back in the 70s during the boom, as well as, of course, many other integrable systems were found during the time period. And in fact, Kortweg and De Vries themselves were able to find one soliton solution, also Knoedel cnoidal wave solutions. But of course, not much was known back then. But owing to inverse scattering transform, we learned a lot of things about the behavior of KdV and other integrable systems. And of course, one would reasonably ask, what is not unknown after more than 50 years, 55 years to be explicit. And I would say that a lot is known when it comes to standard initial conditions, but disproportionately less so otherwise. And in fact, Zakharov, Vladimir Zakharov, one of the founding fathers of soliton theory, repeatedly asked that it's not enough. No standard initial condition. And he posed the question, what happens if the initial data in the KdV equation is neither decaying at infinity or not periodic? And then he asked, can we extend the inverse scattering transform to this case, which has great practical importance? And let us discuss briefly what kind of problems occur when we no longer have standard initial data. Well, first of all, it is perhaps complicated spectrum of the underlying Schrödinger operator, which causes existential problem to scattering theory. And even if we can develop scattering theory, like in my case, the standard scattering data is are no longer data. So the first step in the inverse scattering transform machinery may break down. And however, I'm not going to discuss such situations, but Lex-square need not produce a simple time evolution anymore. And then if we're able to have accomplished the first two steps, inverse scattering theory is not developed outside of standard cases. And last but not least, we don't know if KdV is actually well posed if initial conditions are not standard. Here I only mention briefly the famous Bourgain's theorem, which says that KdV is well posed in L2, and now there is a full scale of L2 based Sobolev spaces where KdV is well posed. But then one could ask the reasonable question, if we can solve KdV only in essentially two cases, why it's more integrable than any other generic PDE? And so can we then call it integrable if you don't know how to integrate it? Those are, of course, very good questions. What Zakharov had in mind, and many other leading experts in the area who pose similar questions. As a matter of fact, KdV is not sensitive to the behavior at spatial minus infinity. KdV is very, very unidirectional. So both infinities contribute differently to the KdV solution. And as a matter of fact, Grutsky and I showed that any condition, any boundary condition can be removed at minus infinity. It doesn't matter as long as our initial data is short range at plus infinities by doing what we call right-sided inverse scattering transform. And now we're getting very close to my main objectives. Well, as a matter of fact, inverse scattering transform breaks down even when the initial data behaves like this. So it's just slightly worse than short range. Because in this case, scattering data, standard scattering data is no longer defines the potential uniquely as was found back in 1981 with specific examples. Also, I would note that if the behavior of the potential or initial data is like this or worse than Coulomb, then dense singular spectrum may fill the positive half line, as was shown by Nabokov in 1987. And then, of course, scattering, any chance of creating scattering problem or developing scattering theory would fail. But at least good news is that KdV remains well posed for any L2 initial profile, as I mentioned before. And now, in about 12 years ago, Vladimir Matveyev wrote in one of his papers a very interesting and solved problem would be to develop inverse scattering transform for potentials which behave at infinity like this. And he also says that related inverse scattering transform is not yet solved, and large time evolution of such initial data is a challenging problem. So I'm going in part address this question. And in general, initial or potentials which behave like this for large X with some A and omega are referred to as Wigner von Neumann type potentials. And the main feature of such potentials is possible embedded bound states at omega squared. And it's the only point of singular spectrum. So the rest of positive spectrum is purely absolutely continuous, but such potentials may have infinitely many negative bound states too. And an example of potential which exhibits a positive bound state is provided by this explicit function, which behaves at infinity, indeed, like sine x over x, and the size of amplitude or quasi amplitude is actually important. And the Schrödinger operator with such potential supports a positive bound state at +1. Wigner von Neumann gave a different example, the famous example in 1929 in the half-line case. And in my 2020 paper, I investigated this initial profile and used well-posers to actually derive explicit formulas for the time evolution of such initial profile under the KdV slope, which gives a hint how inverse scattering transform could actually be adjusted to the setting with the presence of positive bound states. Positive bound states or embedded bound states, those are the same. And a little bit more about general Wigner von Neumann potentials. Again, if we recall what is what, so A is kind of amplitude and omega is a kind of frequency. Then if the absolute value of the quotient of amplitude and frequency is greater than 2, then omega squared may be a bound state, which is known to be very unstable. And an arbitrary small perturbation can turn such bound state into what we call Wigner von Neumann resonance. And if this modulus of this quotient is greater than radical over 2, then infinite negative spectrum may occur, which was demonstrated by Martin Klaus back in 1982. And in general, he actually studied potentials of this form, not behaving like this infinity, but exactly of this form. And he showed that if this quotient is less or equal to 1 over radical 2, then there are only finitely many negative bound states, otherwise infinitely many. All right, with all those introductions out of the way, let me now introduce my main ingredients, which I used in the proof. However, I'm not sure if I would be able to go over proofs, but at least present main ingredients and framework. The first one is Weil solution, which is generalization of the well-known Yost solution. Yost solution is, of course, a well-known thing in integrable system in the community, but Weil solution is not that well-known in this community. And we recall that psi either plus or minus is called right or left Weil solution of the full line Schrödinger equation if it's integrable at plus infinity for plus side and integrable at minus infinity at for minus side for any lambda in the upper half plane. Existence of such solutions is, of course, a good theoretical question, which was solved more than 100 years ago. And the criteria for existence, for uniqueness of such condition is not known yet, however. But if potential Q here is bounded from below or essentially bounded from below, then both Weil solutions exist and essentially unique, meaning that unique up to a multiplicative constant. So the next lemma will play an important role or crucial role in my arguments. And it says the following, that if we have for some energy, the Schrödinger equation has a real solution which is integrable at plus infinity, and if the while function, while solution has the boundary value from above at point E, then the U naught and psi are proportional to each other. Is important statement, not difficult to prove though, and we will also need the famous while M function, which is the log derivative of the while solution, as shown here. And for those who are familiar with Dirichlet to Neumann map more than while M function, then while M function is a one-dimensional analog of the Dirichlet to Neumann map. And the next ingredient would be basic scattering identity or fundamental scattering identity, which is a pretty simple thing, but I would have to go over it to fix my terminology. But first of all, let me state basic conditions which I'm going to impose on my potential Q, which will always be assumed in the statements which follow. That, of course, Q is a regular function, a real regular function. And secondly, the underlying Schrödinger operator is semi-bounded from below. And this holds if the potential is bounded from below. And the third condition is the existence of Yost solution at plus infinity. The last condition means that the pair psi and psi bar forms a fundamental set for the Schrödinger full-line Schrödinger equation, and the Wronskian is equal to 2ik. Of course, it doesn't depend on x, but more specifically, it's 2ik. And so since psi and psi bar form fundamental set, any solution to the Schrödinger equation can be represented as a linear combination of psi bar and psi, including the left while solution, which can be normalized by the following formula, which is called basic scattering identity. The coefficient which appears here is called the right reflection coefficient, and it's symmetric and contractive for almost every case. Next ingredient would be a diagonal Green's function. Recall that if potential Q is summable at plus infinity, then the Yost solution exists and actually continues for any K different from 0. But slower decay at plus infinity may cause spectral singularity of the Yost solution. Those are the points, real points where Yost solution, which is analytic in the upper half plane, would exhibit singularities when you approach the real line. And the diagonal Green's function is defined by this formula, as you know, where we have two solutions, psi plus and psi minus, which in our case can be written down as follows, because the Wronskian at the bottom is 2ik. And what is why Green's function general important? First of all, it is what we call Herklot's function, which it's an analytic function which maps upper half plane to upper half plane, and all poles are simple. It includes isolated poles and what I call embedded poles. And all poles are actually eigenvalues of the Schrödinger operator. And last but not least, I should have here lowercase g. That it behaves for large negative energies like this, which allows one to recover the potential by this formula. And now yet another ingredient, which is of course well known to this audience, is norming constants of negative bound states. So if my potential decays also at minus infinity, so that the Schrödinger equation has the left Gauss solution, then the Gauss solution which I chose would be proportional to Weil solution, which I chose, would be proportional to the Gauss solution, and where the coefficient of proportionality is called the transmission coefficient, and it can be computed by this formula, which is totally trivial, but this formula says that this coefficient is analytic in the upper half plane with simple poles, and poles occur where these two solutions are linearly dependent. And of course, there are the points where we have negative bound states. And those are the points where our diagonal Green's function blows up. And as you know, the reciprocal of the L2 norm of Yost solution, in this case, I'm considering a right Yost solution, but it doesn't matter which one to take, is what we call norming constant of a bound state minus kappa sub n squared. And that's typically how norming constants are introduced, but it's more convenient. In my case, it's actually more convenient once you want to approach inverse scattering, transform from the Riemann-Hilbert problem point of view, can be written down in this form, which is reasonable to call isolated pole condition. So the residue of the Weil function at I kappa n is proportional to the Yost function, right Yost function at I kappa n, and the coefficient of proportionality is exactly I times the square of the norming constant. Well, and this formula gives a convenient way to introduce norming constants of positive bound states or embedded bound states. And so if the potential, as was mentioned before, is not in L2, then depending on how off it is, a resonance or spectral singularities may pop up on the real line, and basically the behavior could be pretty arbitrary. Such, I'm going to deal with singularities which are produced by Wigner von Neumann type potentials, and such singularities are typically referred to Wigner von Neumann resonance. Sorry, there's misprint here. And but in some other communities, they are called spectral singularities. I will call them resonances. And in the Neumann von Neumann, Wigner von Neumann case, resonance was studied in quite detail in the work of Martin Klaus in the 90s. The only thing I'm going to mention here in the connection with his work is that the order to which Yost solution blows up at certain points or points of resonances could be its power, but the power isn't could be arbitrary. Most important, our case would be this kind of blow-up behavior. Now, since the right solution blows up at the real point omega, we may want to, using this pattern, we may set up what we call embedded Poe condition. So the residue of the Yost solution at resonance is proportional to the while solution on the left, and the coefficient proportionality is chosen this way, and will be clear why it's convenient to choose it this way, not just by putting a constant here. Lambda alpha here is a real some real number, and residue here, it's not technically a residue because psi isn't analytic on the real line, but the blow-up behavior is like this, so we can define a residue as the limit, and then this notation becomes totally legitimate. And the last but not least ingredient is what we call gauged transformation. And the following statement will be important in our consideration, that if we have a pair of analytic functions related, or while functions, while solutions, I would say, related by the basic scattering identity, then if we introduce two other functions by this formula with real functions a sub n and some functions f sub n of two variables which are real for real k, actually they could be almost anything, not in my case, but in general, could be anything. Then the pair of functions introduced by this formula will also satisfy the basic scattering identity with the same reflection coefficient. The verification of this claim is totally trivial, and I took the name from a paper of Billman and Miller, and but it, in one form or another, it's been used by many authors. I personally learned about this transform from the Grava-Minakov 2020 paper, but the form I'm going to use it is different. And now we are able to state our main theorem. So this theorem is about Schrödinger operator, not KdV solutions so far. And now let me go over its statement. So besides basic conditions, which I went over before, I add two important conditions. The first condition, I call it resonance, is that the Schrödinger operator or Schrödinger equation has L2 solution at minus infinity for some positive energies. And a continuity condition that the right solution and the reflection coefficient are both continuous at omega n. And omega n again are called resonances. And if these two conditions are satisfied on top of basic conditions, then the function of phi sub n defined by this formula is square integrable at minus infinity. And if we define the Schrödinger operator with the following potential, where a matrix G sub plus is the Gram matrix formed by phi sub n, then such potential supports embedded bound states at resonance points. So I call this theorem turning resonance into embedded bound states because omega sub n for the original potential isn't a bound state, but a resonance point. And some history. So the transform, which appears here, is nothing but the binary Darboux transform, which was introduced back in 1986 by Babbage and Matveev in the context of the KP equation. But what's interesting that under a different name, more specifically double commutation, the same transform appeared back in 1951 and is due to Gelfand and Levitan, where they introduced it while doing the groundbreaking research on inverse spectral problems for Sturm-Liouville operators. And then in 1978, Dye formally introduced what we now call double commutation. This term wasn't used by Gelfand Levitan, and developed, put on a formal basis, which was further developed by the work series of work of Gestesi with collaborators, and more importantly, the last one in the series was due to Gestesi and Teschel in 1996, where they gave complete characterization of double commutation method. And our approach to binary Darboux transform is inspired by the Riemann-Hilbert formalization. And I'm kind of running out of time, so I have to go a bit faster. So now some discussions related to the main theorem. The eigen functions which correspond to the positive eigenvalues can be uniquely found by solving this linear equation. It's a linear algebraic equation on y sub n's. And for n equal 1, the formula becomes particularly easy. And it follows from the main result, then the difference between the original potential, or I would call it background potential, and the potential within embedded bound states is an L1 at minus infinity. And first of all, it is continuous. The difference is continuous. And but decays as 1x at plus infinity. So the new potential is no longer short range at plus infinity. And more specifically, the difference behaves like this. So it's nothing asymptotically, but a sum of Wigner-von types of potential. And the last point in my discussion is that you can't create, if Q sub x is short range at both ends, then you cannot create embedded bound states. You have to have at least one point where the modulus of the reflection coefficient is 1. Outside, it's typically holds for the origin, but I need it for an arbitrary or a different real point. So one important corollary of the main theorem is that if we take short range initial profile, or not initial, potential, which is short range at plus infinity, and then scattering data could be formed and assume that scattering data consists of reflection coefficient, positive bound states, and norming constants. In general, it could be more complicated, but let us consider this simple situation. And this is actually scattering data. It means that it recovers the potential uniquely. Then for the potential wherein embedded bound states are added, the scattering data would contain an extra component made of positive bound states and their norming constants. So in other words, alpha sub n play the role of norming constant, and it answers a question posed to me by Rowan Killip. And the answer is yes. He asked if norming constants are required, and indeed they're required. And now the second important theorem I would like to discuss is time evolution of such initial profiles under the KdV flow. And such solutions could be called bounded positon, and positon was introduced back in the 90s and as a singular solution which has a double pole singularity. And the spectral theorem which corresponds to it has a positive positive eigenvalue. That's why they call it positive positon. So, and back in the 90s, Matveyev asked if they are bounded positons. So once he constructed the singular. And the main theorem, actually, its development can answer this question. So, and the answer is here. So if you formally evolve the potential from the main theorem and the KdV flow, then the KdV solution within bound states can be computed by the same formula. What is interesting in this formula is that it adds extra, the solution gains extra term, which of course accounts for slow decay at plus infinity. And of course, embedded bound states don't change over time, so they remain the same. They don't appear or disappear, which I have to rush a little bit, which answers a question which posed to me by Dmitry Pelinovsky, who asked if they appear or disappear over time. And the answer is no. And also, he was wondering about the type of behavior of a positon solution. And they account for waves which propagate with velocity 4 omega n cubed to the left. So they run in the direction opposite to solitons. And I'm running over time a little bit. So the formula, specifically this formula, is reminiscent to n-soliton formula. So one which looks like this. So the same pattern and the same type of entries in this matrix. However, functions which appear here have only finitely many real zeros, while in my case they have infinitely many. Other than that, formulas are strikingly similar, which suggests that bounded positon interact the same way as solitons. But of course, they're highly oscillatory because function psi has infinitely many zeros. And next important corollary is that the binary Darboux transform doesn't change not only reflection coefficient, but also the transition coefficient. It remains unchanged under the binary Fourier Darboux transform. It means that the momentum it doesn't change the momentum, and it doesn't change the energy. So if you have a background Q such that this integral exists with finite energy, then the energy of the wave with added in positive bound states would not change. And the way we added bound states, we can actually remove bound states, and we can remove positive bound states, not all of them at a time, but only the ones we want to remove, and turn them into resonances. So as a matter of fact, I prove both statements at once, but it's more convenient to state them separately. So positive bound state can be killed. And now I have a few, actually 3 files with proofs for which I don't have time, but I want to show you a picture. Numerical simulation. One positive solution. So it's a numerical simulation. So I had to truncate my potential. So at some level, so it's not actually a Wigner-Neumann type potential. It is it's short range potential, but it exhibits interesting bulb moving to the left. And I still don't know if it's a breather. KdV
Alexei,
breather.
I'm afraid we cannot see your video. I guess you need to change the screen you are sharing.
Oh, okay. Thank you for letting me know. Interesting. Oh boy. You can't.
No,
let me.
Maybe stop sharing your screen and then start again. Are you still with us? Looks good.
Okay. Here's what the picture shows. So initial Wigner-Neumann type potential starts dissolving over time. And the main question, if it's a KdV breather or not, my numerical simulation could not answer that question because I had to truncate my potential. And it typically takes a day to run your computer to get this picture.
So what are the blue and the red lines? What is the solution, the blue or the red line?
I believe red lines. Let me. Yeah, blue. Blue. Red line is envelope.
Okay, thanks.
And Yefim Pirinovsky asked me if bounded positon could be modeled for a rogue wave, shallow rogue wave. Well, the picture, my simulation suggested that it could. If you know that KdV equation is invariant with respect to switching time and the coordinate, so meaning that you can come up with an initial profile which would over time exhibit a large amplification of the amplitude. But I don't know much. I'm still working on all that. Thank you. Thank you so much for your attention.
Okay, thanks for your nice talk. Questions?
It's Mount McKinley, unrelated to solitons.
So did those envelopes in the numerical plot mean you have long time asymptotics for this initial data?
Yeah, well, you know, it's decaying. Yes, but it certainly behaves differently than a regular dispersive waves. But how differently they behave remains an open question. How they interact is yet another thing which needs to be investigated. The main problem is that once you apply the Riemann-Hilbert problem methods, then the machinery developed by Dite and Zhou breaks down because at points of interest, reflection modulus of reflection coefficient becomes 1. It means that the typical transformations which are used in the Dite Zhou machinery break down.
Okay, thank you.
Further questions? Okay, that